Hello and welcome to this lesson on diffraction, which is part of the waves topic in Module 4 of Electrons, Waves and Photons for OCR A-Level Physics. So if we've been successful and we've learnt in today's lesson, we should be able to understand what diffraction is, describe the diffraction pattern made when light passes through a single slit, and understand how to demonstrate diffraction using a ripple tank. So we're going to be looking at the following part of the OCR A-Level Physics specification, 4.4.1. Wave motion. Now diffraction is a property which is unique to waves, and diffraction is the process of the wave spreading out as it comes through a narrow gap or around an obstacle, as shown in the following image. Now diffraction can be easily observed through water waves in a ripple tank. Now objects can be placed into the ripple tank to create a barrier with a gap in the middle of it. The gap can be varied to see the effects that this has on the wave spread through the tank. Now all waves will diffract. Now during diffraction, the speed, the wavelength and the frequency of a wave do not change when diffraction occurs. Now the amount of diffraction depends upon the wavelength of the wave compared to the gap size it moves through. Now when the gap is a lot bigger than the wavelength, diffraction is not noticeable. You do get noticeable diffraction when the gap is several wavelengths wide, and the most diffraction is when the gap size is the same size as the wavelength of the wave. Now if the gap is smaller than the wavelength, the waves mostly reflect and do not diffract. Now sound waves will diffract a lot when they move through a door frame, as the wavelength of the sound wave is about the same size as that of the door frame. But visible light waves will not diffract when moving through a door frame, as the light wave has a much smaller wavelength than the gap of the door frame. For visible light waves to diffract, they must pass through a very small gap or slit. Now light shone through a narrow slit can produce a diffraction pattern. Now to get a clear interference pattern, you should use monochromatic light, which is coherent. Now monochromatic light is a light source containing a single wavelength and frequency. If light is not monochromatic, it has numerous wavelengths and frequencies, so different wavelengths will diffract by different amounts, the red light diffracting the most, so the pattern produced will not be very clear. Now to get monochromatic light, you either place a filter in front of the white light or use a laser source, so a laser will give a clear pattern. Now as a laser beam is coherent, it is very powerful and can damage your eyesight. You should never shine a laser towards a person or off a reflective surface. You should always wear safety goggles when using a laser and have a warning sign on display. Also, the laser should never be left on when not in use. So visible light shone through a narrow slit can produce a diffraction pattern as shown on the screen here. And you can see an image taken of a diffraction pattern produced when a red laser light is passed through a single slit. Now if the wavelength of a visible light wave is of similar size to the slit or aperture, you will get a diffraction pattern of bright parts maxima and dark fringes minima. Now this fringe pattern is due to something called interference taking place after diffraction. The pattern has a bright central fringe, a central maxima, with alternating bright and dark fringes on either side of it. The bright fringes, or maxima, occur due to constructive interference. The waves from across the width of the slit arrive at that point on the screen in phase. The dark fringes, or minima, occur due to destructive interference. The waves from across the width of the slit arrive at that point on the screen completely out of phase. Now if you use visible light that is not monochromatic, different wavelengths will diffract by different amounts and you won't get this clear interference pattern. You can do a similar experiment using a white light source and a set of colour filters instead of using a laser. So as we said before, visible light shone through a narrow slit can produce a diffraction pattern, as shown here and on this image of the screen. Now when visible white light is shone through the slit, the different wavelengths are diffracted by different amounts. The longer the wavelength, the greater the diffraction. So the visible red light diffracts the most. The visible blue light diffracts the least. So you can see here the difference in diffraction patterns from the red light and the blue light that comprise white light. Now this tells us that instead of getting clear fringes, you get the spectra of colours at each maxima in your diffraction pattern. But this is not observed at the central maxima, as this is white. So to summarise what we've looked at in today's lesson, we've looked at the diffraction of all waves and the techniques and procedures used to observe diffraction using ripple tanks. So if we've been successful and we've learnt in today's lesson, we should be able to understand what diffraction is, describe the diffraction pattern made when light passes through a single slit, and understand how to demonstrate diffraction using a ripple tank. So thank you for watching this lesson on diffraction, which is part of the waves topic in OCR A-Level Physics Module 4, Electrons, Waves and Photons. Thank you so much and have a lovely day.